Students, so welcome back to my video lecture 8 on p block elements. Okay, so what did we do in video lecture 7? Yes, we started with some of the important compounds of boron. Okay, and I have listed out all the important compounds of boron, which are that. Okay, that is borax. What is the formula for borax? Na2B4O7.10H2O. we discussed its structure, we discussed its chemical properties, and we were talking about a very important test called as Borax Bead test, isn't it? Okay, Borax Bead test. Okay, now in this video we will continue with Borax Bead test, and then we will look into the other compounds of boron like boric acid and diborane. Okay, yes students, let us continue with what? Borax Bead test. Okay, yes, Borax Bead test. Okay, by the way, I told you, okay, what does borax bead consist of? Borax bead consists of what? NaBO2 plus B2O3. Please look into my previous video and try to understand, okay, what is borax bead and how is it formed. Okay, clear? Yes. So what is borax bead? It is a white transparent, it's a transparent glassy appearance. It has a transparent glassy appearance, just like I told you, just like marbles. The way, have you observed marbles, the one which kids used to play it? Okay, so just like marbles, it's a transparent glassy bead. Okay, what is the composition of that borax bead? It is NaBO2 plus B2O3. Are we clear? Okay, yes. Look here, but borax, see, I forgot to tell you this, Na2B4O7.10H2O, isn't it? This is called as borax. Well, borax is a white crystalline solid. This is a white, crystalline. It's a white crystalline solid. This is a white crystalline solid. Okay, crystalline solid. Okay, and from this borax we will get borax bead. When it is heated, okay, it loses all its water molecules, and when heating is continued and then cooled, we will get a transparent glassy bead, and this transparent glassy bead is called as what? Borax bead. And I have also told you what is the important use of this borax bead. Okay, using this borax bead we can detect metal ions present in the salt. Which metal ions can be detected? Transition metal ions can be detected, transition metals can be detected using borax bead test. Okay, what is that we are supposed to do is, we are supposed to heat the salt with this borax bead. Heat the salt with the borax bead in the flame. Okay, just like Bunsen flame, or else normal candle flame. Got it? Okay, take the salt in the borax bead and heat it in the flame. Look here, the flame consists of two parts. Okay, the flame, there are two flames. Look here, yes, one will be like this, isn't it? Okay, this is the flame, and there will be one more inner flame, isn't it? One more inner flame. Well, this is called as what? Oxidizing flame. Okay, and this is called as reducing flame. Okay, reducing flame. Are you getting my point? This is reducing flame, and this is going to be what? Oxidizing flame. So when salt, with the borax bead is kept in this flame, when it is heated in the flame, different colors are produced in the reducing flame as well as in the oxidizing flame. Different metal ions of transition elements will produce different color in the reducing flame as well as in the oxidizing flame. The color will be different both in reducing flame as well as what? Oxidizing flame. For example, look here. Let us see some of the metal ions which impart different colors in different flame, that is oxidizing flame and reducing flame. I told you we can detect what? Transition metal ions like what? Chromium, then iron, then cobalt, then nickel, and then what? Copper. See, what are the colors in oxidizing flame? What are the colors in oxidizing flame? And what will be the color in reducing flame? Please remember this because it's going to be very important for your NEET examination. Okay, yes, oxidizing flame and reducing flame. Oxidizing flame and reducing flame. See, chromium will impart same color in both oxidizing flame and reducing flame. What is it? Okay, in oxidizing flame also it is green colored. Okay, in reducing flame also it is green colored. Okay, just like cobalt also, in both oxidizing flame and reducing flame the color will be same, that is blue, okay, and blue. Okay, blue and blue. Okay, whereas if you see iron in the oxidizing flame, okay, it will impart yellow color, whereas in the reducing flame it will give green color. Green color. Are you getting my point? Okay, if you go with nickel, okay, in the oxidizing flame it will give green color, whereas in the reducing flame it will give yellow color. Yellow color. Okay, are we clear? Are you able to understand my point? Okay, yes. And then if you talk about copper in the oxidizing flame it will give blue color, whereas in the reducing flame it will give, okay, red brown color. Are you getting my point? Look at here. So different metal ions, chromium 3+, iron 2+, cobalt 2+, nickel 2+, copper 2+. So these cobalt 3+, okay, so these metal ions, okay, will give different colors, okay, in different flame when they are heated, when their salts are heated along with what? Borax bead. Are we clear? Okay, any doubts with this? Okay, now let us try to write the reaction. Okay, let us try to write the reaction. Say for example, I have copper sulfate. Okay, I have copper sulfate salt. Okay, copper sulfate salt. Now I'm going to treat this with, I'm going to heat it with what? Borax bead. What does borax bead consist of? The borax bead consists of NaBO2, isn't it? NaBO2. Are we clear? NaBO2 plus B2O3. This is from what? Borax bead. Are we clear? Okay, so I'm going to heat this copper sulfate salt with borax bead in which one? Okay, yeah, Bunsen flame. Let us heat it with borax bead in the Bunsen flame. What is going to happen? See, what does NaBO2 consist of? It consists of, copper sulfate consists of Cu2 plus and SO4 2 minus, isn't it? And NaBO2 consists of Na plus and BO2, okay, minus. Yes or no? Yes. Now what are you supposed to do? You're supposed to, okay, interchange the ions and apply crisscross method, and what are the products formed? We will be getting CuBO2 twice plus Na, apply crisscross method again, Na plus SO4 2 minus, you will be getting what? Na2SO4 plus B2O3 This compound will be blue colored, okay, in the Bunsen flame. Okay, that is in the oxidizing flame, this compound is going to be blue colored. That is why, okay, oxidizing flame will be imparted with which color? Blue color. Understood? So I hope you can write the reaction for borax bead test. Any doubts with this? Okay, so that's guys, that's all about borax, the chemical properties of borax, the structure of borax, okay, and also borax bead test. Okay, see, in the very beginning I have told you that, okay, we will be talking about the different, okay, allotropes of boron. Yes, let us talk about the different allotropes of boron. Very important again. Again it is important. Okay, look here, boron exists in two allotropic forms. Okay, boron exists in two allotropic forms. One is amorphous boron, okay, amorphous boron, okay, and the other one is crystalline boron. Okay, amorphous boron, and the other one is what? Crystalline boron. Are you getting my point? Yes. So there are two allotropic forms of boron. Which are the two allotropic forms of boron? Yes, one is okay, amorphous boron and crystalline boron. So guys, now the preparation of amorphous boron is important, and also the preparation of crystalline boron is important. So we have to understand the preparation of amorphous boron and crystalline boron. It is very, very, very important, okay, in terms of your NEET perspective. Got it? Okay. So how do you prepare amorphous boron? Okay, how do you prepare amorphous boron? So for that, what you're going to do is, we have to take boric anhydride. What is the formula for boric anhydride? B2O3. Okay, now let us treat this with boric anhydride with magnesium. Okay, when boric anhydride is treated with magnesium, yes, magnesium will reduce boric anhydride to boron, and it itself gets oxidized to what? Magnesium oxide. When boric anhydride is treated with magnesium, magnesium will, okay, reduce boric anhydride to boron, and it itself gets oxidized to magnesium oxide. Look here, what type of boron did we get? Yeah, we got amorphous boron. What type of boron is it? Amorphous boron. So how do you prepare amorphous borons, guys? Okay, when boric anhydride is treated with magnesium, magnesium will reduce boric anhydride to boron, and it itself gets oxidized to magnesium oxide. Okay, very nice. Now how do we prepare crystalline boron? Okay, very simple again. Very simple. What we are supposed to do is take the trihalides of boron, any trihalide. So what are the different trihalides of boron? We have boron trifluoride, boron trichloride, boron tribromide, okay, and boron triiodide, isn't it? Okay, so out of this trihalides, you take any trihalide of boron. For example, I am going to take boron tribromide. Boron tribromide. Now treat this boron tribromide with what? Okay, hydrogen. Let us not worry about balancing the reaction. So balancing the reaction is not our concern here. We just have to understand the reaction. We just have to understand what are the products formed and what are the byproducts formed here. Okay, so now what I'm going to do is, if I have to prepare crystalline boron, I'll be taking what? The trihalides of boron, treat it with hydrogen. Okay, yes, in the presence of tungsten wire. Okay, which wire is it? What does W refers to? Okay, W is nothing but tungsten. So you are treating, okay, trihalides of boron with hydrogen, okay, in the presence of tungsten boron, okay, tribromide, okay, yes, boron tribromide will be reduced to boron, and hydrogen will be oxidized to what? Hydrogen bromide. Boron tribromide will be reduced to boron, and hydrogen is oxidized to, okay, hydrogen bromide. Okay, so look here, what type of boron did we get? What type of boron is it? We will be getting what? Crystalline boron. Okay, so in this case we got amorphous boron, and in this case we got what? Crystalline boron. How do you prepare crystalline boron? When trihalides of boron is treated with hydrogen in the presence of what? Tungsten wire. Okay, oxidation reduction takes place, giving rise to what? Crystalline boron. Amorphous and crystalline. Okay, these are the two allotropic forms of boron. Okay, any doubts with this? So we have prepared borax, we have finished borax, and we have finished the allotropic forms of boron. Okay, now what is the other yes, okay, compounds of boron? Again, I'm talking about a very important compound of boron. A very, very important compound of boron. Which is that important compound? That is boric acid. Yes, boric acid. What is the formula? Okay, I'm talking about the third compound of boron. What is it? Okay, boric acid. What is the formula of boric acid? It is H3BO3, isn't it? This is H3BO3 is called as boric acid. I can write it as H3BO3, or else I can also write it as BOH thrice. Are we clear? Okay, I can write it as H3BO3 or BOH3 thrice. Understood? Okay, students, how do you prepare boric acid? Okay, what are the different methods of preparation of boric acid? Yes, How do I prepare boric acid? Okay, any idea? Yes, we have already learned the preparation of boric acid. How do I prepare boric acid? Okay, see, hope you remember this. Look here. Okay, Na2B4O7. What is Na2B4O7? Sodium metaborate, correct? Okay, yes, isn't it? Na2, or else that is borax. Borax. Na2B4O7 is borax. Now, what happens when borax is hydrolyzed? What happens when borax is hydrolyzed? Very simple. Come on. Okay, yes, so you know what I have told you, you have to interchange the ions. So I have Na2B4O7. In Na2B4O7 I'll be having what? Na plus B4O7 2 minus, and in water we'll have what? H plus and OH minus. Now interchange the ions. Na plus OH minus will give what? NaOH. Okay, NaOH. Now what else? Okay, you apply crisscross method, H plus 2 minus. So apply crisscross method, I'll be getting what? H2B4O7. H2B4O7. What is this? Yes, H2B4O7. But we know, okay, when it is heated slightly, okay, yes, when this H2B4O7 is heated, it will be giving H3BO3. Is it correct? Okay, it will be giving what? H3BO3. Okay, H3BO3 is nothing but orthoboric acid. Okay, so I can directly write it when borax is hydrolyzed with water. Okay, so I'll be getting sodium hydroxide and what? Boric acid. I can directly write this. Okay, I'll be getting what? Okay, sodium hydroxide and boric acid. The solution that contains sodium hydroxide and orthoboric acid is slightly basic in nature. It is basic in nature. Okay, the solution containing sodium hydroxide and boric acid or orthoboric acid is basic in nature. Why it is basic in nature? Because sodium hydroxide is a strong acid. Sodium hydroxide is a strong acid. Okay, orthoboric acid is a weak acid. Orthoboric acid is a weak acid. Sodium hydroxide is a strong base. Sodium hydroxide is a strong base. Orthoboric acid is a weak acid. Strong base, weak acid, we know. Okay, the mixture of strong base and a weak acid will be basic in nature, correct? The mixture of strong base and weak acid will be what? Basic in nature, because basic character dominates the acidic character, since it is strong acid and strong base and weak acid. Okay, so therefore the mixture of sodium hydroxide and boric acid, okay, is basic in nature, because sodium hydroxide is a strong base, whereas boric acid is a weak acid. Okay, look here. So our concern is to prepare what? Orthoboric acid. Okay, our concern is not to prepare sodium hydroxide. So what is that I'm going to do is, okay, so instead of now carrying out this reaction, what I'm going to do is I'll treat, okay, borax Na2B4O7, okay, with water and HCl. Okay, Na2B4O7 plus water will give NaOH plus H3BO3, isn't it? NaOH plus H3BO3. This NaOH will combine with HCl to give rise to what? NaCl plus H3BO3. Look here, we got a salt, okay, and we got a weak acid. Therefore now the solution is going to be acidic in nature. The solution is going to be what? Acidic in nature. Okay, understood? Okay, the solution is going to be what? Acidic in nature. Okay, if I don't use acid HCl there, the solution is going to be basic in nature. But if I use HCl in the reaction, the solution is going to be acidic because of the formation of what? Salt. Because of the formation of salt. Understood? This is one method of preparation of boric acid. What is that? When borax is hydrolyzed, or when borax is hydrolyzed with acid, okay, we will be getting boric acid and boric acid. Is there any other method for the preparation of boric acid? Yes, there is another method. What is it? Okay, hydrolysis of halides of boron. Okay, hydrolysis of trihalides of boron. Hydrolysis of, okay, let's say for example any trihalide. I told you boron forms boron trifluoride, boron trichloride, Boron tribromide and boron triiodide, isn't it? Okay. Now take any trihalide, for example, boron tribromide. Now you hydrolyze it. Okay, when boron tribromide is hydrolyzed, what is that I'll be getting? I'll be getting H3BO3 plus HBr, isn't it? What is this? Boric acid. Okay, boric acid. Okay, any doubts with this? Now guys, what are the properties, what are the physical properties of boric acid? Okay, what is its structure? Very important, very important. Okay, so let us understand the physical properties of boric acid. Physical properties of boric acid, H3BO3. Physical properties of H3BO3. Okay, look here. See, H3BO3, okay, it's a, yes, H3BO3 is a, okay, Lewis acid. It's a Lewis acid. Okay, it's a weak acid. It's a weak acid and it's a monobasic acid. It's a monobasic acid. Okay, look here, understand these 3 points. Okay, H3BO3 is a Lewis acid, H3BO3 is a weak acid, and H3BO3 is a monobasic acid. Okay, why it is a Lewis acid? Okay, say if I have the structure BOH, okay, 3, this is the structure of BOH thrice, or else H3BO3, isn't it? Now look here, boron is surrounded by how many electrons? 1, 2, 3, 4, okay, 5, 6. Well, boron is surrounded by 6 electrons. It is deficient of 2 more electrons to complete its octet. Therefore the boron is electron deficient. Since boron is electron deficient, it is ready to accept electrons. It acts as electron acceptor. Okay, we know very well electron acceptors are nothing but what? Lewis acids. Okay, electron acceptors are nothing but Lewis acids. Any doubts? Clear? Okay, no doubts. Now okay, it's a weak acid. It is a weak acid, no doubt in it. Why it is a monobasic acid? Okay, yes, H3BO3. Okay, what do you mean by this monobasic acid? Okay, yes, look here, yes, understood. Please understand this carefully. Okay, why H3BO3 is called as monobasic acid? Why it is a monobasic acid? What is monobasic acid? Okay, yes, what is monobasic acid? Okay, what do you mean by basicity? Okay, yes, what is basicity? Okay, see, for acids we define basicity, and for bases we define what? Acidity. It's reverse. We define what? Acidity. Okay, for acids we define basicity, and for bases we define what? Acidity. Okay, what do you mean by basicity now? Okay, basicity means number of, okay, H plus ion. Okay, number of H plus ions released by an acid when dissolved in water. When dissolved in what? Water. Are we clear? Okay, basicity means number of H plus ion released by an acid when dissolved in water. For example, look at here, sulfuric acid, H2SO4. When I dissolve it in water, it will give what? 2 H plus ions and SO4 2 minus, isn't it? Okay, so sulfuric acid is donating what? 2 H plus ions in water. Therefore, what is the basicity of sulfuric acid? It's 2. Therefore, we call the sulfuric acid as a dibasic acid, isn't it? Sulfuric acid is called as a dibasic acid. Why it is called as dibasic acid? Okay, yes, this is called as dibasic acid. Why is this called as dibasic acid? Because it can donate 2 H plus ions in an aqueous solution. So that is why it is called as what? Dibasic acid. And how about phosphoric acid? H3PO4. H3PO4, okay, will donate what? 3 H plus ions when dissolved in water. Okay, yes, it will donate 3H plus ion when dissolved in water. Since it is donating 3H plus ion, it is a tribasic acid. It's a tribasic acid. Understood? Yes. Okay, so phosphoric acid is a tribasic acid because it donates what? H plus ion in aqueous solution. Okay, sulfuric acid is a dibasic acid because it donates what? 2H plus ion when dissolved in aqueous solution. How about HCl? HCl will donate what? 1H plus ion when dissolved in water. That therefore HCl is a monobasic acid. HCl is a monobasic acid. So what is basicity? It is the number of H plus ion released by an acid when dissolved in water. When dissolved in water. Are we clear? Okay. Now I am telling that okay, boric acid is monobasic acid. Okay, boric acid is monobasic acid. Why boric acid is monobasic acid? Look at here. Boric acid has 3 hydrogens, isn't it? Okay. Boric acid has 3 hydrogens. Okay, that means will it release 3H plus ions in water? No, it will not release 3H plus ions in water. If it had released 3H plus ions in water, it would have become tribasic acid. But okay, boric acid is not a tribasic acid. It is what? Okay, monobasic acid. It's a monobasic acid. Why it is a monobasic acid? Even though it has 3 hydrogens. Even though it has what? 3 hydrogens. Why it is monobasic acid? Next, let us try to understand. Look here. Okay, yes, I have what? Yes, H3BO3, boric acid, isn't it? Boric acid. We know this is a Lewis acid. It can accept electrons, okay, because it is deficient of electrons, 2 electrons. Okay, is that correct? It is electron deficient. Do you want me to explain it again? No, I don't think so. Okay, boron is surrounded by 6 electrons. Okay, boron requires 2 more electrons to complete its octet. Therefore boron is okay, electron deficient. Hence boric acid will act as what? Lewis acid. It can accept 2 more electrons to complete its octet. Correct? Okay, now this boric acid when dissolved in water, H2O, okay, what is going to happen? Okay, look here, there will be vacant b orbitals in boron. Okay, there will be vacant p orbitals in boron. Look, now oxygen, we know oxygen has 2 lone pair of electrons. Correct? Okay, when boric acid is dissolved in water, okay, oxygen will donate a lone pair of electrons to what? Vacant orbital of boron. Oxygen will transfer its lone pair of electrons to the vacant orbitals of boron. When oxygen transfers its lone pair of electrons to the vacant orbitals of boron, it forms a coordinate bond with boron. Okay, well, look here, it is going to be like this. Yes, okay. When oxygen forms, okay, when oxygen donates a pair of electrons, a lone pair of electrons to the vacant orbital of boron, okay, oxygen will form a coordinate bond with boron. Okay, since oxygen has lost its lone pair of electrons to boron, oxygen is going to get positive charge, and since boron has gained a pair of electron, boron is going to get what? Negative charge. Now what will happen? Okay, so this hydrogen will get eliminated. Hydrogen is going to get eliminated. So what is the product formed? Well, look here, it will be giving OH, okay, whole negative, okay, plus H plus. So therefore, how many H plus ion is released in water? How many H plus ion is released in water? Only 1 H plus ion is released in water. Isn't it correct? Okay. When boric acid is dissolved in water, 1 H plus ion is dissolved in water. 1 H plus ion is dissolved in water. Sorry, 1 H plus ion is released in water. Therefore, okay, boric acid is what type of acid? It's going to be a monobasic acid. Understood? Okay. And now boric acid is not releasing its H plus. is it releasing this H plus? Is it releasing this H plus? Is it releasing this H plus? No, no. Okay, please understand my point. Boric acid will not release its H plus. Okay, which H plus is released? Okay, the H plus of water is released. This H plus, okay, this hydrogen is released. This hydrogen belongs to what? This hydrogen belongs to water. Okay, so note this point. When boric acid is dissolved in water, it will not release its H plus, but okay, when what water forms a coordinate bond with boron, water will lose its H plus ion. Water is going to lose its H plus ion. So the point to be noted here is boric acid, no doubt it's a lowest acid. It's a lowest acid, but okay, boric acid is not an Arrhenius acid. Okay, boric acid is not an Arrhenius acid. It's not an Arrhenius acid. Why it is not an Arrhenius acid? Because it is not donating its H plus. If it is donating its H plus, it's going to be an Arrhenius acid, but it is not donating its H plus. Instead of donating its H plus, it is donating the H plus of what? Water. Therefore, okay, no doubt boric acid is okay, lowest acid, but it's not an Arrhenius acid. Okay, students, in the next video we will be talking about the structure of boric acid, and then we'll go with diboron. Okay, thank you.